Hi friends, welcome to Coordinate, and today we want to understand the shortest job first scheduling algorithm. Now, a shortest job first scheduling algorithm can either be a preemptive type of scheduling algorithm or a non-preemptive scheduling type of algorithm. So, in this session, we'll base more attention on the preemptive type of it as a scheduling algorithm, and on the next session we'll understand a non-preemptive scheduling algorithm. So to define shortest job first as simply a scheduling algorithm, this is an algorithm in which the process having the smallest execution time is chosen for the next execution. Shortest job first. The process with the shortest or the smallest execution time, it is the process that will be executed by the CPU. And when it comes to the words preemptive, definitely we expect a switch to be happening by the CPU. The CPU can be checking, of course, in the ready queue and to see if there is any other process that has arrived, and if we have a new process with the shortest, of course, execution time, which is the best time, then definitely that process will be executed by the CPU. Then the process that was running by the CPU, that was being executed, will go back in the ready queue to wait, of course, for it to become the smallest of the processes that are already in the ready queue. So it is sometimes called, which is the shortest job first, it is sometimes called shortest remaining time scheduling algorithm. So here is a question. Let's see how this question can be handled and how we can answer this question. So we have a number of processes that have been given to us with their respective arrival time. So we have process 1, which is definitely one of the processes. The arrival time is 0 millisecond. It arrived at 0.0. And then we have, of course, process 2, which arrived at the time when the CPU was already executing, at the time the CPU executed for 4 milliseconds. And then we also have process 3, which arrived by the time the CPU had, of course, executed for 2 milliseconds. And then we have process 4, which arrived by the time the CPU had already executed for 3 milliseconds. Now, take note of their burst time. The burst time definitely just denotes the total execution time for each of the processes. Process 1 burst time is 7 milliseconds. Of course, process 3 burst time is 10 milliseconds. Process 4 burst time or total execution time is 2 milliseconds. If we were to ask ourselves now, which one has the smallest burst time or execution time? Definitely we would say process 4 has the smallest execution time, followed by process 2, followed by process 1, followed by process 3. The question is, calculate the average waiting time for all the processes. Though it is shortest job first based on a preemptive scheduling algorithm, our attention needs to focus on their arrival time and the total burst time or execution time for all the processes. So meaning, definitely process 1 should execute first because it arrived in the ready queue by the time when process 4, which is the process with the lowest execution time, wasn't already in the ready queue. So definitely, by the time process 4 was coming in the ready queue, the CPU was working. I mean, the CPU shouldn't be dormant, no. It was working because we had, of course, a process with the largest burst time already in the ready queue by the time when no process was in the ready queue. Let's consider the Gantt chart and see how we can represent this information in the Gantt chart, which is simply a visual representation of the shortest job first on a preemptive scenario now of the processes, for it to see how we can represent each and every process based on their arrival time and their execution time. Don't forget, shortest job first. The shortest execution time should be handled first, of course, for as long as it is in the ready queue. So let's see how a Gantt chart will, of course, make us understand vividly and easily what is happening on these processes. So here I've just copied the processes. We have process their arrival time, and of course the burst time, or which is of course the execution time needed for each and every process. So in the Gantt chart, this is how we can plot a Gantt chart. Process 1 of course started the execution, though it doesn't have the shortest execution time because it was the only process in the ready queue. Hence the CPU at point 0 didn't proceed and double check on the other processes execution time. No. Why? Because process 1 was the only process in the ready queue. So process 1 starts at point 0 and it reaches of course 3 milliseconds. The CPU executes for 3 milliseconds. Don't forget, by the time the CPU was reaching 2 milliseconds, if you take note on process 3 also arrived in the ready queue. If this is the ready queue, then definitely we can say, okay, process 1 was already in the ready queue, which is process 1. And by the time we had process 1 in the ready queue, the CPU of course had to execute for 2 milliseconds, then process 2 also arrived in the ready queue. By this time the CPU was reaching of course 3 milliseconds, process 4 also arrived in the ready queue. So now the comparison on the first job first, the execution time and the like, should now be based on 4 processes: process 2, process 4 and process 1. But by the time the CPU reached 2 milliseconds, why didn't we proceed now on executing process 3? Because it also arrived in the ready queue. Oh, don't forget, shortest job first. So here by then of course the CPU executed for 2 milliseconds, hence here we remain with the total execution time as 5. But the CPU didn't proceed on executing process 3 because process 3 total execution time is greater than the total time that remained for process 1 to execute. Hence process 1 had to continue execution up to 3 milliseconds. By the time process 1 reached 3 milliseconds, definitely also process 4 showed up now in the ready queue. Here we also had process 4. And then the CPU had to double check again. Okay, I'm executing process 1, which now has the remaining time since it executed for 3 minus 7, which now had 4 milliseconds as the total execution time remaining. Okay, I'm executing process 1. Now I have 2 processes newly into the ready queue. We have process 4 now with the burst time or the execution time as in 2 milliseconds. Okay, should I continue executing process 1? The answer was a no. Why? Because the execution time for process 4 was less than the execution time that remained for process 1. I mean 4 and a 2. Definitely we can tell that a 2 is less compared to 4. Hence, no. Let me not continue executing process 1. Let me execute process 4. Hence, process 4 had to execute consecutively for 2 milliseconds because there was no other process in the ready queue that was less than 2 milliseconds. Hence, it had to execute for 2 milliseconds, meaning from 3 milliseconds up to 5 milliseconds. And then from there, we also had process 2 again ready in the ready queue. By the time the CPU reached 4 milliseconds, I mean 4 should be somewhere here. So by the time the CPU reached 4 milliseconds, then definitely also process 2 was already in the ready queue by then. So process 2 now in the ready queue. Now the question was, okay, so I'm at 4 milliseconds. Should I stop and execute process 2? The answer was a no. Already executed for 1 millisecond. So we had 1 millisecond as the total execution time for process 4. So should I proceed? Yes, it had the shortest execution time for compared to all the processes, and it had to execute up to 5 milliseconds. Then process 4 was completely executed because it only had 2, of course, execution time as the best time for the entire process to completely be executed. And then from there we remain with process 1, process 2 and process 3. Since we are at 5, processes are already in the ready queue because we can tell that these numbers are of course less than 5. So which process should I execute first? Don't forget, process 1 executed for 3 milliseconds, hence the remaining is 4. And process 2 didn't of course do any execution, it has 3 milliseconds. And then from there we can tell that, okay, the process 3 also has 10 milliseconds. So which process is having the shortest job first? Definitely it is process 2. Hence process 2 had to execute again from 5 to 8, which is 3 plus 5, which is 8, for 8 milliseconds, and it is of course also completely executed because it is done. Ready queue is now having process 1 inside the ready queue, and of course process 3 inside the ready queue, and process 1. Which one now between process 3 and process 1 is having the shortest execution time, shortest best time? Here we have 10, and here we have 4 because it already executed for 3 milliseconds, and definitely it is process 1. So process 1 had to take the CPU for 4 milliseconds from 8 to 12, and lastly we have process 3 now executing because it was by then the only process remaining in the ready queue, so no need to even double check for the other processes. It had to execute for 10 milliseconds, which is the total best time for process 3. So this is how we can present this work into the Gantt chart. Don't forget, we are doing it on a preemptive part. The switching things where it is switching from process 1, process 4, process 2, process 1 to process 3, that is what we call preemptive. It is double checking the CPU. Okay, is there any other process with less best time compared to the process being executed? And if their answer is yes, then definitely that process should come into the CPU. So this is what has happened now. So what we need now to understand is, for we to calculate the total average waiting time for each and every process, we need definitely to find the waiting time for each and every process, and then from the waiting time for each and every process, that is where we will now extract the average waiting time for all the processes. Because average, it's add up the waiting time for each process and then divide by the total number of processes. Now to calculate the waiting time for each and every process, there is a formula that we need to understand. This is the actual formula, unlike for the first come first serve, the scheduling algorithm which we had in our previous session. Here on shortest job first, based on a preemptive, there is a formula which is waiting time for each process is equal to last waiting time minus the milliseconds executed before minus the arrival time for the process that we are working on. So if we were to calculate now the waiting time for each and every process, so we would say, okay, what is the last waiting time for process 1? Last waiting time, not the previous waiting time, So process 1 waiting time, first waiting time was 0, but this isn't the last one. No, it again executed. So the last waiting time is 8. Okay, then what is the total number of milliseconds that it executed before? Process 1 had to execute for 3 milliseconds before the final execution. So we'll say, okay, 3, it had to execute for 3. And then what is the arrival time for process 1? From the question we were given, 0. So minus 0. Definitely the total waiting time for process 1 is 5 milliseconds. And then process 2, again the same formula applies. What is the last waiting time for process 2? Well, process 2 only had to wait for 5 milliseconds. We don't have process 2 again here. So it's 5. Then what is the total number of milliseconds executed before? It didn't execute before. We only have process 1, process 4, process 2, and this is the only time when it executed. So it didn't execute, which is a 0. Then what is, of course, the arrival time for process 2, which is 4. As the time we've been given in the question, hence we didn't do the computation, we have 1. Then for process 3, definitely the last waiting time is 12. Definitely total number of time executed before is 0. Then total waiting the arrival time, definitely we have a 2. When we do the computation, that is equal to 10. Then for process 4, what is, of course, the last waiting time? Process 4 only had to wait for 3 milliseconds. We don't have process 4 again here. Then from there, what is the total number of milliseconds executed before? It didn't execute, hence we have a 0. What is now the arrival time in the question given? It's 0. So definitely we have a 0 when we do the computation. Hence now we can calculate the average waiting time. Average meaning all these waiting times for each process. When you add, then divide by the total number of processes, which is 4. And here is the actual average waiting time. 5 as a waiting time for process 1, 1 as a waiting time for process 2, 10 as a waiting time for process 3, 0 as the waiting time for process 4. Add up and then divide by 4. What is the average waiting time? Definitely the average waiting time is 4 and the units definitely have milliseconds because they are being executed in milliseconds, which is ms. So this is the actual representation we can represent on the shortest job first as a scheduling algorithm based on a preemptive understanding of shortest job first. Now let's proceed and see how we can represent the same scheduling algorithm, which is shortest job first, now based on a non-preemptive scheduling algorithm. Preemptive, the CPU was switching back and forth. Now non-preemptive, of course we expect the CPU not to be switching from back and forth. Let's proceed on our next session, and please don't forget to subscribe moreover you are on Coordinate.